this lecture we will be looking at the simplex algorithm to solve linear programming problems. In the last lecture we looked at the algebraic method and we said that the algebraic method should have 3 important characteristics. 1, it should not evaluate any infeasible solution. 2, it should be capable of giving better and better basic feasible solutions, and 3, it should be able to identify the optimum when it is reached and terminate. We will now see the simplex method which does all the 3, and we first see an algebraic form of the simplex method and then we will see the tabular form of the simplex method in this lecture. Let us take the same example and explain how the simplex method works for this problem. So as usual we convert the inequalities to equations by adding a slack variable, which we have done here. Slack variable has 0 contribution to the objective function. So solving this problem is the same as solving this problem. Now first thing we need in the simplex method is that it should, since the simplex method should not evaluate any infeasible solution, we need to begin the simplex method by considering a basic feasible solution. Now that we can do here easily, the way this problem is, by fixing initially x1 and x2 to 0, so that we get a value of x3 equal to 5, x4 equal to 12 very easily. In fact, one of the important things in any linear programming problem is that the constraints should not have a negative value on the right hand side. If a constraint has a negative value on the right hand side, then we need to multiply this by -1 to make it non-negative. In the process the sign of the inequality may be reversed. So we will make an assumption that in all linear programming problems that we solve, the constraints have a non-negative value of right hand side. It can have a 0, but it should not have a negative. Now because these constraints have a non-negative value on the right hand side, and because every slack variable appears only in one equation, it is now very easy for us to fix the rest of the variables to 0 and have a starting solution with x3 equal to 5, x4 equal to 12, which is basic feasible. It is basic because the variables x1 x2 are fixed to 0. It is feasible, it will be because x3 and x4 as variables appear only in one of the constraints and they have a non-negative right hand side value. So the solution with fixing x1 x2 to 0 and evaluating x3 equal to 5, x4 equal to 12 is basic feasible, and that is the first solution that we will look at. So the first 2 set of basic variables that we will be solving are, we call this first iteration. We are going to solve for x3 and x4 and we are going to fix x1 and x2 to 0. So we rewrite this as x3 equals 5 minus x1 minus x2, x4 equals 12 minus 3x1 minus 2x2, z is equal to 8x1 or 6x1 plus 5x2. What we have done here is we have identified the basic variables, we have now written the basic variables in terms of the non-basic variables, and we have also written the objective function in terms of the non-basic variables. x1 and x2 are the non-basic variables, x3 and x4 are the basic variables. Now we can put x1 equal to 0, x2 equal to 0 to have a solution x3 equal to 5, x4 equal to 12, z equal to 0. Now what are we interested in? We are interested in maximizing this z. Right now this z is at 0 because x1 and x2 are non-basic with 0. Now we want to increase z, we can do that either by increasing x1 or by increasing x2. Both have a positive, strictly positive coefficient and both are at 0. So we can increase either x1 or x2 or both to increase z. What we do in this simplex method is we try to increase only one variable at a time. So we can choose to either increase x1 or to increase x2. Now between the two we would prefer x1 because the rate of increase is higher because it has a bigger or a higher coefficient. So we try to increase x1, x1 is presently at 0. Now there will be a limit on the value that this x1 can take because as we increase x1 we realize that x3 and x4 are going to reduce. They are right now at 5 and 12 respectively. For example, if x1 becomes 1, then x3 will become 4, x4 will become 9. So as x1 increases, x3 and x4 start reducing and coming closer to 0. So x1 can increase up to the point where one of them becomes 0, because increasing x1 beyond that would end up making either x3 or x4 negative, which we do not want. We will be violating these. So this equation will allow x1 to go up to 5, this equation will allow x1 to go up to 4, and the limiting value that you can increase x1 to is 4, which is a minimum of 5 and 4. Now increasing x1 beyond 4 will make this x4 negative and violate this. So now this constraint or equation becomes the binding equation, which is going to determine the value that x1 can take. So we write this again as iteration 2. We now rewrite, we say 3x1 equals 12 minus 2x2 minus x4. x1 is 4 minus 2 by 3 x2 minus 1 by 3 x4. Now we write this again by saying x3 equals 5 minus x1, we go back and substitute 5 minus 4 minus 2 by 3 x2 minus 1 by 3 x4 minus x2. This on substitution would give 1, plus 2 by 3 x2 minus x2 is minus 1 by 3 x2 plus 1 by 3 x4. Now the objective function z becomes 6x1 plus 5x2, 6 into 4 minus 2 by 3 x2 minus 1 by 3 x4 plus 5x2, which on substitution would give us 24. This is minus 4x2 plus 5x2 is plus x2 minus 2x4. Now we have another iteration where your x1 and x3 are basic, x2 and x4 are non-basic. The solution is given by substituting x2 equal to x4 equal to 0, getting x1 equal to 4, x3 equal to 5, z equal to 24. So this is another basic feasible solution that we have obtained. Now this is basic because we are fixing x2 and x4 to 0. It is feasible because of the way we limited x1. We made sure that x1 is getting a non-negative value. We also made sure that neither x3 nor x4 goes to a value below 0. So we ensure that x1 is feasible, x3 and x4 also are feasible, one of them becomes 0 and the other remains at 0. So this is another basic feasible solution that we have evaluated. Now this basic feasible solution has x1 equal to 4, x3 equal to 5, x2 and x4 equal to 0 with z equal to 24. Now our objective is to try and increase this z further. Now this z can be increased further by either increasing x2 or decreasing x4, because x4 has a negative coefficient. Now x4 is already at 0, it is non-basic, it is at 0. So we cannot decrease x4 because decreasing x4 would make it negative, which would violate this. So we do not explore the possibility of trying to increase z by decreasing x4. On the other hand, we can try and increase the z by increasing x2. x2 is already at 0, so by increasing x2 we can try and increase z further. So we try to see whether we can increase z further by increasing this x2, or we try to find out what is the limiting value or the maximum value up to which this x2 can be increased. Now this equation, the first one, would allow x2 to go up to 6, because 6 into 2 by 3 is 4, 4 minus 4 is 0. So when x2 takes a value 6, this would be 0. Increasing x2 beyond 6 would make this negative, we do not want to do that. Now this would make x2 go up to 3, because increasing x2 beyond 3 would make x3 negative, which we do not want. So, the limiting values are 6 and 3 and we take the minimum one. Now, this is the minimum value, x3 is the maximum value, I am sorry, 3 is the maximum value that x2 can take, beyond which this one would become negative and therefore is the limiting value. So, now this is the equation which is going to make x2 come into the basis and take a non-negative value. Now, this is now rewritten here as iteration 3. Now, this becomes 1 by 3 x2 equals 1 minus x3 plus 1 by 3 x4, x2 equals 3 minus 3 x3 plus x4. Now, the next equation is this, x1 equal to 4 minus 2 by 3 x2, 3 minus 3 x3 plus x4 minus 1 by 3 x4. This is on simplification, 2 by 3 into 3 is 2, so you get 2 plus 2 x3, this is minus 2 by 3 x4 minus 1 by 3 x4 is minus x4, and substituting z is 24 plus x2 plus 3 minus 3 x3 plus x4 minus 2 x4, 27 minus 3 x3 minus x4. You get a plus x4 minus 2 x4 would give you minus x4. So, now you have a solution. Now, in this case x1 and x2 are basic, x3 and x4 are non-basic at 0. So, the solution is you substitute x3 and x4 equal to 0 in all this to get x1 equal to 2, x2 equal to 3, z equal to 27. Now, this solution is also basic feasible. It is basic because x3 and x4 are fixed at 0. It is feasible because of the way we defined the limiting value that x2 can take. Now, this is the solution at the end of the iteration 3. Now, we want to see whether we can increase z further. Now, increasing z further based on this expression can be done by decreasing x3 or by decreasing x4, because both have negative coefficients. Now, both is not possible, decreasing x3 and decreasing x4 are not possible because both of them are already at 0 and decreasing them would make them infeasible. So, we are unable to proceed from this point to try and increase z further, and since we are unable to increase z further, we stop here and we say that the best solution has been obtained, and the best solution that we have obtained is x1 equal to 2, x2 equal to 3, z equal to 27. Now, this is the same solution that we got by the graphical method as well as by the algebraic method. If we look at this very carefully, this method has done exactly the three things that we wanted it to do. Number one, it will not evaluate any infeasible solution because we put in that extra effort to find out the limiting value that this variable can take. Therefore, none of the variables will become negative. So, we will not get any infeasible situation. It will evaluate progressively better solutions because every time we are only trying to increase the objective function for a maximization problem from where it is. So, 0 became 24, 24 became 27, and the moment the optimum is reached or the best solution is reached, it will have a way to terminate and say that further increase is not possible. So, you need not evaluate all the 4 basic feasible solutions to get here. Within 3 we were able to reach. The third one has told us already that it is optimal. So, this method is the ideal method that we were looking for with respect to the 3 requirements that we had. This is the simplex method represented in an algebraic form. So, we now see the simplex method in a tabular form. We create a simplex table like this. There are 4 variables that we have. So, we write them as x1, x2, x3, x4. The objective function coefficients are 6, 5, and we also said slack variables x3 and x4 have a 0 objective function coefficient. So, we have 0 and 0. The previous method we started with x3 and x4 as the basic variables. We said we can fix x1 and x2 to 0 to get x3 equal to 5. Remember that this was written this way, and x3, x4 greater than or equal to 0. We started with fixing x1, x2 to 0 as non-basic and started with x3 and x4 as basic variables. So, the basic variables that we begin are written here, x3 and x4. We also have the coefficients corresponding to the basic variables written here. The equations are written as they are. So, you have a 1x1 plus 1x2 plus 1x3 plus 0x4 equal to 5, 3x1 plus 2x2, 0x3, 1x4 equal to 12. This is called right hand side. We introduce another row which we call as Cj minus Zj, and we explain this. Now, what we compute as Zj is for every variable j, we compute the dot product of this and this. For example, Z1 will be 0 into 1 plus 0 into 3, which is 0. C1 is 6. C1 is the coefficient in the objective function for variable x1. So, C1 is 6. So, C1 minus Z1, the number that is going to appear here will be 6 minus 0 into 1 plus 0 into 3, 0. So, 6 minus 0 is 6. In the very first iteration, because this is 0, all the Zj's will become 0. So, Cj minus Zj will be the same as this value. Now, for this it will be 0 into 1 plus 0 into 2, which is 0, 5 minus 0 is 5. Here it is 0 into 1 plus 0 into 0, 0, 0 minus 0 is 0, 0 minus 0 into 0 plus 0 into 1 is 0, 0 minus 0 is 0. When it comes to the right hand side, we do not have any value here. So, we simply multiply 0 into 5 plus 0 into 12, which is 0. Now, we look at the variable which has the largest positive Cj minus Zj, which happens for variable x1. So, now we say that the variable with the largest Cj minus Zj enters the basis. So, x1 enters the basis, and we put an upward arrow indicating that x1 is going to come into the solution. Now, x1 will come into the solution and it will replace either x3 or x4. We need to find out which one it replaces. So, to do that, you create another column called theta, and that is 5 divided by 1, 5, the right hand side divided by the corresponding element of the entering column. So, 5 divided by 1 is 5, 12 divided by 3 is 4. Now, choose the one with the minimum value of this theta. So, this is the variable that goes. Now, variable x4 will leave and variable x1 will enter. Now, the next iteration will now have x1 replacing variable x4. So, you will have x3 and x1 which will come here. Now, variable x1 replaces variable x4. So, you have x3 and x1 coming in. x3 has a coefficient 0, x1 has a coefficient 6. Now, what we need to do is this. If we look at this table, these two were the basic variables or variables which we were trying to solve. Now you need to have an identity matrix corresponding to these variables. x3, x4 in the order of appearance has a 1 0 0 1, which is an identity matrix. Now here we have x3 x1, so in the order of appearance we want an identity matrix. So x3 will have 1 0, x4 x1 will have 0 1 in the order in which the variables appear. To make this happen, we perform some row operations on this table. To do that, we explain the row operations as follows. If you look at the previous table, this is the entering variable, this is the leaving variable. The row corresponding to the leaving variable is called a pivot row. And this particular number, which is the intersection of the entering column and the leaving row, is called the pivot element, which is usually marked with a circle. Now first step would be to divide the pivot row by the pivot element as it is. So I get 3 divided by 3 1, 2 by 3 0, 1 by 3 and 4. Remember we wanted a 1 0 and a 0 1, we have got a 0 here and a 1 here. Now we need to get a 0 here without disturbing this 1, and that is done by using row operations. This value is 1, this value is also 1. The row operation here would be, if I subtract this from this, I would get a 0 here. So 1 minus 1 0, 1 minus 2 by 3 1 by 3, 1 minus 0 1, 0 minus 1 by 3 minus 1 by 3, 5 minus 4 1. So the row operation here, the new row 1 will be the old row 1 minus the new pivot row. That would give us this. Now this is the solution given by x3 equal to 1, x1 equal to 4. Now we compute the Cj minus Zj again. Now this value is the dot product of this and this, 6 minus 0 into 0 plus 6 into 1. So 0 into 0 plus 6 into 1 is 6, 6 minus 6 is 0, 0 into 1 by 3 plus 6 into 2 by 3 is 4, 5 minus 4 1, 0 into 1 by 3 is 0, 6 into 2 by 3 is 4, sum is 4, 5 minus 4 is 1, 0 into 1 plus 6 into 0 is 0, 0 minus 0 is 0, 0 into minus 1 by 3 plus 6 into 1 by 3, 0 into minus 1 by 3 is 0, 6 into 1 by 3 is 2, 0 minus 2 is minus 2, and here we simply multiply the values and write it, 0 into 1 plus 6 into 4 is 24. So we now have a solution, x3 equal to 1, x1 equal to 4, z equal to 24. Now once again we go back and look at the values of Cj minus Zj and identify that variable which has the maximum positive value. That happens for variable x2. So x2 now enters the basis and becomes a basic variable. To find out the leaving variable, we need once again to find out the value of theta, which gives us the limiting value. So that is given by right hand side divided by the corresponding element in the entering variable column, 1 divided by 1 by 3 which is 3, 4 divided by 2 by 3 which is 6. Between the two, the minimum theta happens here. So this variable leaves the basis. In the next iteration, x2 will replace x3, which is written here, x2 and x1 retains its position. Now this is the pivot row, this is the entering column, so this is your pivot element. Now once again, as we did earlier, we need to do row operations such that under x2 we have a 1 0, under x1 I have a 0 1, so that the identity matrix appears in the order in which these variables appear here. and that is done by the same steps that we did in the previous iteration. Divide the pivot row by the pivot element, which is the first thing to do. So 0 divided by 1 by 3 is 0, 1 by 3 divided by 1 by 3 is 1, 1 divided by 1 by 3 is 3, minus 1 by 3 divided by 1 by 3 is minus 1, 1 divided by 1 by 3 is 3. Now I need to bring a 0 here by doing the row operation. Now this row, this is the element, so this row minus 2 by 3 times this would give me a 0 here. So 1 minus 2 by 3, 2 by 3 comes from this. So 1 minus 2 by 3 into 0 is 1, 2 by 3 minus 2 by 3 times 1 is 0, 0 minus 2 by 3 into 3 is minus 2, 1 by 3 minus 1 into 2 by 3 is 1 by 3 plus 2 by 3, which is 1, 4 minus 2 by 3 into 3, 2 by 3 into 3 is 2, 4 minus 2 is 2. So we have completed this. Here we write the objective function coefficients corresponding to x2 and x1 respectively, which are 5 and 6. Now the Cj minus Zj values are 5 into 0 plus 6 into 1, which is 6, 6 minus 6 is 0, 5 into 1 plus 6 into 0 is 5, 5 minus 5 0, 5 into 3 plus 6 into minus 2, 15 minus 12 is 3, 0 minus 3 is minus 3, 5 into minus 1 plus 6 into 1, minus 5 plus 6 is 1, 0 minus 1 is minus 1. Right hand side values are 5 into 3 15 plus 6 into 2 12, which is 27. Now we have a solution with x1 equal to 2, x2 equal to 3 with z equal to 27. We check whether we can improve this solution further by looking at the Cj minus Zj values. Now the maximum positive Cj minus Zj is what we enter. We do not have a positive Cj minus Zj at all. So the algorithm is not able to identify an entering variable. So the algorithm terminates with the solution x1 equal to 2, x2 equal to 3, z equal to 27. So this is called the tabular form of the simplex algorithm. Now if we go back and then we can compare this solution with what we did in the algebraic form, you will realize that we are doing exactly the same three things in the algebraic form. When we began the previous algebraic method, we started with a solution x3 equal to 5, x4 equal to 12, z equal to 0. We had an expression 6x1 plus 5x2, and we wanted to increase based on increasing x1 or x2. We increased x1 because it had the largest coefficient or the largest rate of increase. The second solution that we obtained was this solution x3 equal to 1, x1 equal to 4, and the value of the objective function was 24x1 plus x2 minus 2x4. So this is the solution that we got in the algebraic form, and then we entered x2, and then we finally got 27 minus 3x3 minus x4. We said that we cannot enter x3 or x4 because they will become negative, and we terminate. So whatever we have done in the algebraic method is exactly the same that we do in this tabular method. The only difference is in the algebraic method these two equations would look like x2 equal to 3 minus 3x3 plus x4. Now here we write it as x2 plus 3x3 minus x4 equal to 3. So the tabular form is exactly what we did as the algebraic form, except that we do not write the variables every time we did as we did in the algebraic. Tabular is a very convenient way of representing all the numbers. So this tabular form of simplex method is more popular than the algebraic form, because when we work out the problem by hand, we do not have to repeat writing the names of the variables. So this would give a certain structure to the simplex method of solution to a linear programming problem. Many versions of the tabular form exists different books might give different versions. In some places you will find that you have another row here where you explicitly calculate this Zj, and then you have another row which does Cj minus Zj. There are versions where instead of Cj minus Zj you calculate Zj minus Cj, and then you enter variables accordingly. But what we will do in this course is we will stick to this kind of a tabular format with only evaluating one additional row here, which we call as a Cj minus Zj rule. Our entering rule will be any positive variable or any variable which has a positive value of Cj minus Zj can enter, as x1 entered here and x2 entered here. Here you have all the Cj minus Zj's are 0 or negative, so we do not have an entering variable. So our termination condition is when Cj minus Zj is all less than or equal to 0, for a maximization problem the algorithm will terminate and the best value will give the optimum solution. Now there are a few more things that we need to understand from the simplex table. Simplex table also tells us a few more things, and as we progress in this course we will realize that there are many more things to be understood from the simplex table. We will start with something like this. Now when x3 and x4 are basic variables, you will find that the Cj minus Zj values for the basic variables is always 0. Here x3 and x1 had Cj minus Zj values 0. Similarly x2 and x1, so Cj minus Zj values will be 0. So you do not have to explicitly compute the Cj minus Zj for the basic variables. You need to compute the Cj minus Zj's only for the non-basic variables, which is what we did in the algebraic method. The Cj minus Zj only for the non-basic variables need be computed, and if all of them become negative, the algorithm will terminate. If one of them is positive, then that variable can enter. The limiting value which we found out in the earlier method is exactly the value of theta that we obtained. In the very first iteration, if you go back, you would realize that these were the limiting values. We chose the minimum. Here also we did the limiting values. The only difference is in the algebraic form you would see all these coefficients multiplied with a minus 1, simply because we have shifted the equation sign to the variable here. Now let us take another example for the simplex algorithm, and then we work out a different problem. The problem is to maximize 6x1 plus 8x2, x1 plus x2 less than or equal to 10, 2x1 plus 3x2 less than or equal to 25, x1 plus 5x2 less than or equal to 35. We convert these inequalities to equations by adding slack variables x3, make it an equation x4 plus x5 equal to 35. The contribution of the slack variables to the objective function is 0. So we have 0x3 plus 0x4 plus 0x5. Now we construct the simplex table here with 5 variables x1, x2, x3, x4 and x5 with the right hand side values given here. The coefficients are 6, 8, 0, 0, 0. We start with x3, x4, x5. The corresponding objective function coefficients are 0. Now the equations are written as x1 plus x2 plus x3 plus 0x4 plus 0x5 equal to 10, 2x1 plus 3x2 0, 1, 0 equal to 25, and 1, 5, 0, 0, 1 equal to 35. Now you see the identity matrix under x3, x4 and x5 in the order of appearance 1, 0, 0, 0, 1, 0 and 0, 0, 1. We calculate Cj minus Zj. x3, x4 and x5 are basic variables, so they will have Cj minus Zj 0. For x1 it is 0 into 1 plus 0 into 2 plus 0 into 1, which is 0, so we get 6 here. 0 into 1 plus 0 into 3 plus 0 into 5 is 0, so we get 8 here. 8 minus 0 is 8. Now the non-basic variable which has the largest Cj minus Zj enters, so variable x2 will enter. Now to find out the leaving variable we need to find out a theta. Theta values will be 10 divided by 1 10, 25 divided by 3 is 25 by 3, 35 divided by 5 is 7. Now the minimum value is 7, so this is the leaving variable, x5 is the leaving variable and this is our pivot element. Now in the next iteration x2 replaces x5, so you have x3, x4 and x2. The values are 0, 0 and 8. Now the first step is to divide the pivot row by the pivot element, so that we get the identity matrix. Now we need a 1 0 0, 0 1 0 and 0 0 1 under x2. So we need a 1 here, so divide by the pivot element to get 1 by 5, 1 0 0, 1 by 5 and 7. Now we need a 0 here and a 0 here. So this, the first row of the previous iteration has a 1, so this row minus this row would give us a 0 here. So 1 minus 1 by 5, 4 by 5, 1 minus 1 0, 1 minus 0 1, 0 minus 0 0, 0 minus 1 by 5 minus 1 by 5, 10 minus 7 is 3. We need another 0 here, so this row minus 3 times the pivot row would give us 0, 3 minus 3 times 1 will give 0. So the rule is this row minus 3 times the pivot row would give us a 0. So 2 minus 3 by 5 is 10 by 5 minus 3 by 5, which is 7 by 5. 3 minus 3 times 1 is 0, 0 minus 3 times 0 is 0, 1 minus 3 times 0 is 1. This minus 3 times this, 0 minus 3 times 1 by 5 is minus 3 by 5, 25 minus 3 times 7 is 4. So now we compute the Cj minus Zj values. x3, x4 and x2 are the basic variables, so 0, 0 and 0. We have to compute Cj minus Zj for the non-basic variables x1 and x5. Now this is 0 into 4 by 5 plus 0 into 7 by 5 plus 8 into 1 by 5 is 8 by 5, 6 minus 8 by 5 is 30 minus 8, 22 by 5. Now this is 0 into minus 1 by 5 plus 0 into minus 3 by 5 plus 8 into 1 by 5 is 8 by 5, 0 minus 8 by 5 is minus 8 by 5. 0 into 3 plus 0 into 4 plus 8 into 7 is 56. Now among or between the two non-basic variables x1 and x5, x1 has a positive value, only one has a positive value, so x1 enters. So x1 enters the basis. We need to find out the leaving variable. Now to do that we compute this theta again. 3 divided by 4 by 5 is 3 into 5 by 4, which is 15 by 4. 4 divided by 7 by 5 is 4 into 5 by 7, which is 20 by 7. 7 divided by 1 by 5 is 35. Now we need to find out the smaller one between 15 by 4 and 20 by 7. So 15 by 4 will become 105 by 28, 20 by 7 will become 80 by 28. So 20 by 7 is smaller than 50 by 4, so this is more than 3, this is less than 3, so 20 by 7 is smaller and this becomes the pivot element. Now we need to get x1 here, so we have x3, x1, x2. Now we need x1 comes here, and so we need a 0, 1, 0 here. So the coefficients will be 0, 6 and 8. So divide by the pivot element to get 1, 0, 0, 5 by 7 minus 3 by 7, 20 by 7. Now I need a 0 here and I need a 0 here. So this minus 4 by 5 times this will give me a 0. So this becomes 0, 0 minus 4 by 5 into 0 is 0, 1 into 4 by 5 into 0 is 1, 0 into 0 minus 4 by 5 into 5 by 7 is 4 by 7, so minus 4 by 7, minus 1 by 5 minus 4 by 5 into minus 3 by 7. So minus 1 by 5 plus 4 by 5 into 3 by 7. So minus 1 by 5 plus 12 by 35. So minus 1 by 5 minus 4 by 5 into minus 3 by 7 would give minus 1 by 5 plus 12 by 35. So this will become 5 by 35, which is 1 by 7. So you get a 1 by 7 here. 3 minus 4 by 5 into 20 by 7. So 4 by 5 into 20 by 7 is 16 by 7. So 3 minus 16 by 7 is 5 by 7. So you get a 5 by 7 here, and we need to get a 0 here. So this minus 1 by 5 times this will give me 0. So this is 0, 1, 0. This minus 1 by 5 into 5 by 7 is 0 minus 1 by 5 into 5 by 7 is minus 1 by 7. 1 by 5 minus 1 by 5 into minus 3 by 7. So 1 by 5 plus 1 by 5 into 3 by 7, which is 1 by 5 plus 1 by 5 into 3 by 7 is 3 by 35. So it is 10 by 35, which is 2 by 7. This minus 1 by 5 times this. So 7 minus 1 by 5 into 20 by 7. So this will become 4 by 7. So 7 minus 4 by 7 is 45 by 7. Now the Cj minus Zj values will be 0, 0 and 0. We need to look at only the other two. This is 0, 6 into 5 by 7 is 30 by 7, minus 8 by 7 is 22 by 7 with a minus sign. This is 6 into minus 3, minus 18 by 7 plus 16 by 7 is minus 2 by 7, but 0 minus 2 by 7 is plus 2 by 7. 20 into 6 is 120, 45 into 8 is 360, so 360 plus 120 is 480 by 7. Now we realize that this variable can enter, that is the first thing. So first important thing is, if we go back into the simplex table, you realize that a variable x5 that had left the basis earlier can actually re-enter, which is what we are seeing in this example. It is not absolutely necessary that once a variable leaves, it cannot enter, it can enter. What we are interested in the simplex method is not whether an individual variable appears in the basis. What we are actually interested is the combination that appears in the basis. So a variable x5 which left the basis earlier can now enter again, so which happens here. So to find out the limiting value, 5 by 7 divided by 1 by 7 is 5, 20 by 7 divided by minus 3 by 7. This is the first time we are encountering a negative value here when we are dividing. Till now we had all positive values, so we could divide comfortably and get all the thetas. Now the rule is, if you get a negative value or a 0 here, you do not compute the theta. Theta value is computed only when the entering column has a strictly positive value. The right hand sides will always be non-negative. So theta cannot be negative, theta cannot take indeterminate form, theta cannot be 0 by 0 or something by 0. So we evaluate theta only when this number is strictly positive, so that we get a non-negative value for theta. So we do not evaluate, we put a dash. 45 by 7 by 2 by 7 is 45 by 2. This is the minimum. So this is the pivot element. Now we continue very quickly to go to the last table. Now x5 replaces x3. So you have x5, x1, x2, 0, 6 and 8. pivot element is 1 by 7, divide the pivot row by the pivot element or multiply by 7 to get 0, 0, 7, minus 4, 1, 5. Now we need a 0 and a 0 here. So this plus 3 by 7 into this will give me 0. So 1 plus 0 into 3 by 7 is 1, 0, this plus 3 by 7 is 3, this plus 3 by 7, so 5 by 7 plus 3 by 7 into minus 4, so 5 by 7 plus 3 by 7 into minus 4, so 5 minus 12 is 7, so minus 7, so I get a minus 1 here, this is 0, this plus 3 by 7, so 20 by 7 plus 15 by 7, 35 by 7 which is 5, and here I need a 0, so this minus 2 by 7 times this will give me a 0. So I have 0 minus 2 by 7 into 0 is 0, 1 minus 2 by 7 into 0 is 1, 0 minus 2 by 7 into 7 is minus 2, minus 1 by 7 minus 2 by 7 into 4 is minus 1 by 7 plus 8 by 7 which is 1, this is 0. Now 45 by 7 minus 2 by 7 into 5, so 45 by 7 minus 10 by 7 which is 35 by 7 which is 5. Now Cj minus Zj will be x1, x2 and x5 are basic, we need to evaluate only for these two. 0 into 7, 6 into 3 18, minus 16 is 2, 0 minus 2 is minus 2, minus 6 plus 8 is 2, 0 minus 2 is minus 2, value is 6 into 5 plus 8 into 5 which is 70. Now both the non-basic variables have a negative Cj minus Zj, the algorithm terminates. Now what are the new things that we have learned? Number 1, in this example we realize that a variable that already left the basis which is x5 can re-enter the basis. The only uniqueness is every iteration should have a different combination of basic variables. That is what simplex algorithm ensures. It is not unduly worried about whether a particular variable leaves the basis or enters the basis. Second thing is, when we compute this theta, we do not compute the value of theta when you have a negative or a 0 here. The theta value computed should be strictly non-negative. Therefore when this is negative or 0, we do not compute. The equivalent in the algebraic is theta is the limiting value that this entering variable can take, such that beyond which this particular basic variable will become negative. Now a negative here implies that you can increase this x5 to any value and the present variable x1 will not become negative. Therefore this dash actually implies infinity, but we do not indicate it as infinity, we just leave it as a dash. As a rule you do not compute theta when you have this. And the third point is, in some sense right through you would have observed that we have not represented any of these numbers in a decimal form, and we had actually represented all of them in a fractional form. For example, when we do this we might be tempted to write some of these as decimals, and decimal form can create rounding of errors. You realize that all these fractions finally became nice integers in the end. So it is customary not to represent any of these numbers in decimal form, but to represent them only in fraction form. Now there are other things that we need to learn. So far we have seen only a maximization problem with all constraints of the less than equal to type. How do we address minimization problems? How do we address greater than or equal to type constraints? So those things we will see with different examples in the next lecture.